Welcome back to the second part of this lesson where we're going to convert our ideal body weight into energy estimation. Before we can plan appropriate diets or interventions, we need to understand how much energy a person needs. So we'll start with the Dietary Reference Intakes, or DRIs. These are guidelines developed by the National Academies of Science, Engineering, and Medicine to help us estimate nutrient and energy needs for healthy individuals. And they're essential in government programs like the Dietary Guidelines for Americans, SNAP, and the School Lunch Program. The DRIs serve as general reference values used to plan and assess nutrient intake of healthy people. And within the DRI system, there are two major categories to understand. First, we have the Estimated Energy Requirement, or EER. This tells us how many calories someone is likely to need each day to maintain energy balance. So in other words, it helps us estimate how much energy a person uses based on factors like age, sex, height, weight, and physical activity. Then there's the nutrient intake, which includes macronutrient distribution and micronutrient requirements. Macronutrient requirements are given as a percent of total calories. This includes carbohydrates, proteins, and fats. On the micronutrient side, you'll see categories like RDA, ERR, AI, and UL. And these help determine how much of a vitamin or mineral someone needs and at what point too much might become unsafe. But we'll cover that more specifically in the next video. In this part, we're going to focus on the energy side and how to approximate energy needs. The Estimated Energy Requirement, or EER, is the average number of calories someone needs each day to maintain their current body weight. I've also seen it called TDEE, or Total Daily Energy Expenditure. Essentially, it's based on the idea of energy balance, or how much energy is consumed versus how much is used. And there are three components that make up total energy expenditure. The first is basal metabolic rate, or BMR. This is the energy required to keep the body functioning at rest. Things like breathing, circulation, and temperature regulation. And it makes up the largest portion, around 75% of daily energy use. Next, we have the thermic effect of food, or TEF. This is the energy the body uses to digest and absorb nutrients. It's a small but important component. And then finally, we have the physical activity level, or PAL. This includes everything from structured exercise to everyday movement like walking, fidgeting, and even standing. Together, these three factors determine someone's overall calorie needs. And though we can measure EER, more commonly, we estimate it. The kcal per kilogram method is a quick and practical tool often used in clinical settings. It uses a range of calories per kilogram. And yes, it's another equivalent statement. Mifflin St. Jeor, or MSJ, on the other hand, is a formula-based method that includes height, weight, age, and sex. And it gives us a more individualized estimate. We'll also explore calorimetry, which uses actual gas exchange data to measure energy expenditure. See, calorimetry is the most precise but least accessible way to measure energy needs. And there are two types of calorimetry: direct calorimetry and indirect calorimetry. Direct calorimetry measures the heat produced by the body in a controlled environment, like a respiration chamber. While this measurement is extremely accurate, it's also expensive and rarely used outside of research settings. Indirect calorimetry is more practical and it's also more common. It estimates energy expenditure by measuring the amount of oxygen someone breathes in and the amount of carbon dioxide they breathe out. From this, we can calculate something called the RQ, the respiratory quotient. RQ gives us information about what type of fuel the body is using. An RQ of 1 is pure carbohydrates burning. It means that the patient is burning their carbohydrates to function. An RQ of 0.7 suggests that the person is burning pure fats. Protein lands somewhere in the middle, and if they are burning a mixed proportion, we get a value somewhere in the middle. By looking at gas exchange and understanding the RQ value, we can determine how many calories a person is burning even at rest. We'll come back to RQ when we get into our MNT module on lung disorders and critical conditions like ventilator dependence. But for now, let's practice with the math. This problem says we have a 64-year-old female patient who is 5 feet 4 inches tall and weighs 190 pounds, undergoing direct calorimetry. Her estimated calorie needs are 1,550 calories per day, using 25 to 30 kcals per kilogram and MSJ. Determine which approximation is most accurate for this patient. So what this problem wants you to do is compare 25 to 30 kcals per kg and MSJ to the actual needs that this patient has from direct calorimetry. Pause it, try using kcals per kg, try MSJ, and I'll be here to walk you through it. All right, I'm going to start with the kcals per kilogram, and we know that this patient weighs 190 pounds. We need to convert that 190 pounds into kilograms. So we need to do some dimensional analysis. Do you know the equivalent statement for kilograms and pounds? 1 kilogram is 2.2 pounds. Since this patient is 190 pounds, we want to get rid of pounds by putting it in the denominator right here. LB is pounds. Pounds cancels out, and we find out that a 190 pound person is 86.4 kilograms. Now, the equivalent statement is 25 to 30 kcals per kilogram, and we know she weighs 86.4 kilograms. This right here is my equivalent statement. So we could write that we need 25 kcals per every 1 kilogram, or we could say that for every 1 kilogram, this patient would need 25 kcals. And then we would have to do the same thing with 30 kcals per kilogram. So since this patient is 86.4 kilograms, we would say that she needs 25 to 30 kcals per kilogram. So first you would do 86.4 times 25, kilograms cancels out, and you get 2,159. And then you would just repeat the process with 30 kcals. And when you do 86.4 times 30, you come out with 2,590. This is way higher, 1,000 kilocalories a day, way higher than her measured needs using direct calorimetry. Let's try MSJ. In MSJ, we also need the weight in kilograms, but we need the height in centimeters. And this patient is 5 feet 4 inches. So as I've done before, I'm going to convert 5 feet into inches. 5 feet is 60 inches, and she's 5 feet 4 inches. So I converted 5 feet, that's 60 inches, and then I added on those extra 4 inches. So this patient is 64 inches tall. But we need the height in centimeters. So we have to convert our inches into centimeters. And this patient is 162.6 centimeters. Using dimensional analysis, inches cancels out, and there's 2.54 centimeters in 1 inch. Okay, so now we know that this patient, this 64-year-old female patient, who is 5 feet 4 inches tall, but we know that that's actually 162.6 centimeters. And yes, she is 190 pounds, but that's 86.4 kilograms. Now we know what we need for MSJ. Have you been working on memorizing the MSJ equation? Well, if you haven't, it's time to start. MSJ says that you can estimate the energy needs by multiplying 10 by the weight in kilograms, 86.4, adding 6.25 for every centimeter, and subtracting 5 from the number of years. And then for women, subtracting 161. So we'll take 10 times 86.4, 6.25 times the height in centimeters, and subtract 5 times their 64 years, and then subtract 161 from the end. We get 1,399, which is far closer to the 1,500 kcals per day that were measured using direct calorimetry. Far less than the 25 to 30 kcals per kilogram. Let's try one more. This problem says that we have a patient eating a diet of near pure protein and has an indirect calorimetry test run. From that test, it's determined that the patient breathes out 200 milliliters of carbon dioxide each second. And so how much oxygen must the patient be breathing in? This is a tricky one. You need to know the RQ formula, which is the volume of CO2 breathed out divided by the volume of oxygen breathed in. And then since we're talking pure protein here, we have an RQ value of 0.82. With that, you should be able to identify your values and plug them in. You try. So if my RQ is 0.82, because this patient is eating a diet of near pure protein, we can plug that in for my RQ. And we know that the patient is breathing out 200 milliliters of CO2. So that's my numerator, volume of CO2. We're solving for the amount of oxygen that's inhaled. So if we plug in what we know, the RQ is 0.82, We know that they're breathing out 200 milliliters each second, and we're solving for the bottom. This is going to take some algebra here. If I want to solve for this bottom, V, which we could call X, we need to get it out of the denominator. It's stuck to 200 by division. So we have to undo division. That's multiply both sides by the volume of oxygen. And when we do that, the volume of oxygen cancels out. And we're left with 200 equals 0.82 times V. But we want this V. So we need to undo multiply, meaning we have to divide both sides by 0.82. When we divide both sides by 0.82, 0.82 cancels out over here, and we get volume of oxygen inhaled on its own. And we find out that if her RQ is 0.82, because she's eating a diet of near pure protein, and she's breathing out 200 milliliters of carbon dioxide each second, then she's breathing in 243.9 milliliters of oxygen each second.